Good morning. Is it good? You hear me? So this is the fourth day. We are all getting tired. So I don't know how to bring it, but I have only... Oh, I have also good news. I have good news and bad news. Good news is there are no proofs. But bad news is it's very technical today. Yet another good news is I didn't have strong coffee this morning, which means that I'm going to be very slow. So that's because my brain works very slowly, so I'm not going to rush. So, all right, what am I going to do today? Yesterday, the first day was about a particular way of addressing data-driven control problems. Namely, one uses fundamental lemma, which requires persistently exciting inputs and allows one to parameterize all trajectories of the unknown system. And based on that parameterization, one can attack different kinds of control problems. And then the second day, we made a radical departure from this idea of using persistently exciting inputs and introduced a certain framework, which we call data informativity framework, which allows us to formulate and solve all sorts of problems. First, we looked at the exact data case. There's no noise on the data, and some analysis problems and some design problems we solved. And yesterday, the third day, Henk introduced the notion of quadratic matrix inequality to solve problems in which data is corrupted by noise. Okay? And in particular, he focused on one problem: stabilization by state feedback. Okay? And the crux was a certain tool from quadratic matrix inequalities, matrix S lemma. And he also mentioned the cookbook for data-driven control problems with noise-corrupted data. I'm going to, today I'm going to discuss 3 problems. The first one is H-infinity control. And this is to show that not only feedback stabilization, but pretty much every problem we encounter in systems and control for model-based case can be solved within this framework. But for certain problems, it's not as easy as feedback stabilization. One needs to massage the problem a little bit, because initially it doesn't look like we can use matrix S lemma. That's one thing. And the other 2 problems I'm going to look at are variations on matrix S lemma. Sometimes we don't we don't reach a point where we can apply matrix S lemma, but there are some techniques we need to use to be able to matrix S lemma. Okay? And so today's menu: first, H-infinity control, beyond stabilization, then the technique of dualization for dissipativity analysis, and projection for stabilization from input-output data. The third part is also interesting in the sense that we always used state data. And everyone knows that it is not a plausible assumption that we can access the entire full state in applications. Well, so the last bit is about data-driven control from input-output data. Okay. First, I want to very quickly go over yesterday's lecture, but very quickly. So, at a certain point yesterday, Henk introduced this model class where we have an extra term W, which corresponds to a certain process noise. And we have a true system given by unknown AS and BS matrices, and W being noise is also unknown. Then we have to make an assumption on the noise, obviously. We made an assumption that the noise satisfies a certain quadratic matrix inequality. Henk showed typical examples which we can cover with such a matrix inequality, energy bounds and instantaneous noise bounds and so on. Now this phi is a certain symmetric matrix. Henk also talked about its properties and so on. I'm not going to talk about them again. But then this leads to a set of data consistent systems, which is given by a quadratic matrix inequality. Any pair AB satisfying this quadratic matrix inequality can produce the data for some noise that satisfies the blue quadratic matrix inequality. As you remember, how do I obtain this green quadratic matrix inequality? From here, I solve W and substitute it here, and that gives me the green one. So this is the set of data consistent systems. And because of the assumptions we made on the phi matrix, I'm not going to go into the details, but phi 2 needs to be less than or equal to 0. There is a kernel condition. The Schur complement with respect to phi 2 needs to be positive semi-definite. Because of those conditions, this set is an ellipsoid in the space of AB, dimensions of AB matrices. You can think of it as an ellipsoid. Okay? All right, this is the set of data consistent systems. And we have a certain problem. Yes, as yesterday Henk discussed, this is the problem we have seen. We call the data informative for quadratic stabilization. If there is a feedback gain K and a positive definite matrix P such that this Lyapunov inequality is satisfied for all AB in sigma. If this is the case, then K stabilizes all systems in sigma, because A plus BK is going to be stable as it satisfies this Lyapunov inequality. On top of it, they are going to, all A plus BKs are going to have the same Lyapunov function. Okay? Now, if I look at this Lyapunov inequality, I see that I can cast it as a quadratic matrix inequality in terms of A and B. Indeed, if you multiply these three matrices, you are going to get the left-hand side of star. Okay? Now, what do we want? We want any AB that satisfies the green quadratic matrix inequality to satisfy the blue one. If we can guarantee that, if every AB that satisfies green satisfies also the blue, then we are done. Well, that is what we want. Agree? How can we make sure, how can we verify that every AB that satisfies the green one satisfies also the blue one? That's the question. Okay. And there comes the matrix S lemma, which says that under certain conditions, like n2 to less than 0 and Schur complement greater than or equal to 0, then this is satisfied for any Z satisfying the green one, if and only if, and this holds if and only if there exists a scalar, non-negative scalar alpha, such that m minus alpha n is positive definite. Okay? So essentially, this green quadratic matrix inequality is always fixed if we start within this framework. It's about data consistent systems. Right? And the blue one depends on the problem we are looking at. If the problem we are looking at is feedback stabilization, then this quadratic matrix inequality pops up. But if I have another problem, which I can cast as a QMI in terms of AB, I can still use the matrix S lemma to solve that problem. Because this result, as you see, is a very general result. It's a result about matrices. So whenever I have some other problem, which I can cast as a QMI in terms of A and B, then I'm done. Agree? Because then this blue matrix is going to change, but thanks to this result, I'm going to be able to formulate necessary and sufficient conditions. Right? This is a, but then the issue, we have a very good tool now, or we have a good recipe from the cookbook. It says, this is going to be your base ingredient. It is the set of data consistent systems. It says, if somebody gives you another problem, try to put it in quadratic matrix inequality. Once you do it, apply matrix S lemma. So the issue is then, given a certain problem, to recognize whether we can come up with a quadratic matrix inequality. That's the first one. And secondly, we need maybe different versions of matrix S lemma, because as you see, the green matrix inequality has non-strict inequality here, but the blue one has strict. And we will see later on that in some problems, we have also non-strict here. But as long as I can obtain the blue quadratic matrix inequality from the given problem, then I am I am in business. Okay? Now, today everyone is tired. No, there are no questions. Or maybe I'm doing a great job explaining it so well. Huh? Henk did a great job yesterday, and everybody understood. H. Shall I hold it? Test.
Yes.
Test. Test. Okay. Test. Is there any other one? Yeah, that's okay. No, it's okay. But bring your hand microphone.
Okay.
Test. Yes. I'm back. Bring the hand microphone. Test. So I'm going to look at Test. This one. Okay. Shall I test it? Okay. This one, but this doesn't work, does it? Test. But it works. So there you can hear it. Are you sure? Test. And how about this one?
This one works perfectly.
Okay, let's use this one.
But there is a limitation that you have.
I know. I will try to remember. I use the board then?
Then
I will use the board and then from here I will use it.
let me just try to fix this one. You can just
Stop. Can you switch this one? All right, this one seems to work apparently, although I don't feel like it works. Okay, it does work. H infinity control. Huh? Well, H infinity control is typically studied in continuous time. It is necessary and sufficient. By ordinary, you mean vector eslemma. Like for vector eslemma, there is also a condition on n that it needs to be indefinite or at least positive at a point, right? And for the non-strict, yes. There are a couple of issues here. To begin with, we have an ordinary eslemma and the matrix eslemma. For the ordinary eslemma, there are two versions, non-strict, strict, depending on the sign here. And depending on which one you are looking at, you need extra condition. For the matrix one, you need even stronger conditions. Then it becomes necessary. And so, yeah, exactly. Otherwise, they are always sufficient. To become a necessary condition, you need extra assumptions. So H infinity control we study typically in continuous time. Today we are going to look at discrete time, H infinity control. So I'm going to first very briefly review what H infinity control is. I don't know, especially master students probably didn't see H infinity control before, because it is not taught everywhere. I mean, our students don't see it. Most of them don't see it. But it is the kind of, it was the kind of ultimate control problem. Maybe I should say a couple of words about it. Personally, I feel like there are two, it was a very important moment, I feel like, solution of H infinity control. Before it was solved, control area was dominated by more mathematical problems. Like H infinity control is one of them. And even before, there was an era where geometric approach was very popular, not only for linear systems, but also for nonlinear systems. And when H infinity control was perceived some long time ago, and it was not solved, everybody was trying to solve it from one way or another. And then finally it was solved, and then there are no mathematical problems left in control area. And after it was solved, late 80s, our area became dominated by large application areas. There was a time where biological systems was very popular, and then hybrid systems were very popular, and then network systems were very popular, and now that is data, games. So that's why it's an important problem. It was the last problem, major problem to be cracked in our area. So what is this problem about then? Well, first I need to introduce H infinity performance. I need to define what I mean by H infinity performance. Okay. H is for Hardy, by the way. These are Hardy spaces. And when we talk about Hardy, the next name is Ramanujan, of course, because Hardy is the one who discovered, in a way, Ramanujan. Anyway, so this little L2 is a sequence subspace. Z plus is non-negative integers. So these are sequences. They are RQ valued. They are vector sequences. And they are square summable. So if I take the norm of each VT, square, sum, overall T, then that is finite. So this is the space of all RQ valued square integrable sequences. Is this clear? And we can define this sum, well, it's square root, as the norm of this sequence V. Huh? So we have now a norm on this infinite dimensional space. What is the relation to systems and control? So suppose I have this very simple input state output system. X is the state. Let's treat W as output for the moment. And Z is a certain output. If A is stable and the initial condition is 0, then the output is going to be square summable whenever the input W is square summable. That is easy to see if one writes down if one writes down the output in terms of input and AC matrices. Okay? So basically then, this system, if A is stable and X0 is X0, can be seen as an operator. For every L2 signal W, it generates another L2 signal Z. So I can see it as an operator from L2 to L2. Huh? And then I can talk about the norm of that operator in the following sense. I take the supremum of Z over all W unit norm. And that is called the H infinity performance of this system. But why are we interested in this all of a sudden? Now imagine that this W is a disturbance. Then the smaller this value is, the better it is for us. Because this value tells how much disturbance is amplified in the output. Is this clear? There are no, of course, control input terms yet, but this is how we define H infinity performance. Again, we have to make sure that A is stable, otherwise it is not even defined. Okay. Now, how can I check whether this system has certain H infinity performance? Well, there is the well-known discrete time bounded real lemma, which says if I take a positive gamma, and then I can prove that A is stable and the H infinity performance is less than gamma if and only if there exists a P satisfying this linear matrix inequality. P is an unknown here, and all others are known. Therefore, this is a linear matrix inequality. All right? Is this clear? Now, since I am looking at a linear matrix inequality, I immediately guess if I pose this as a data-driven control problem, I should be able to use matrix S lemma. Because if you remember feedback stabilization, there was the Lyapunov inequality, and we put it in the QMI form, and that was it. So whenever I see an LMI, then I feel like, okay, this is going to work. Tamam. But gamma is fixed, huh? Gamma is fixed. But gamma is fixed. But even if it is not fixed, I can take it gamma square as an unknown. Huh? But it is fixed in this particular case. We are not trying to find the minimum value. Given gamma, we want to check whether the H infinity performance is less than gamma. Then it's an LMI. Huh? Okay. Now, first I look at a design problem. Now, if I start from this system, where U is control variable, control input, and if I choose a feedback, then in the closed loop system, I'm going to look at this system, which looks like the one before. And due to the lemma I have shown, AB is stable and this system has H infinity performance less than some given gamma, is equivalent to this matrix inequality. So the problem here is, given this system, to find a state feedback such that this A plus BK is stable, and this system has H infinity performance less than gamma. Right? I simply changed A to A plus BK, C to C plus DK in the previous matrix inequality. Agree? Now this is going very well, I would say. Huh? It's nice. So this is the model-based scenario. Let's look at database scenario. In the database scenario, I want to write this matrix inequality into a quadratic matrix inequality. Right? Let's look at the 1-1 term here. It contains P minus A plus BK transpose P times A plus BK and some other terms. But let's look at the first two summends here. Huh? Even the second one. If I look at the second one, it is equal to the right-hand side, but I cannot write this as a QMI in AB. And the reason is there is K on right of B here. Huh? There's no way that I can write this as a QMI in AB, right? Because there's K here. Because it has to be something AB, something like AB, a matrix times AB related matrix transpose. So it is not going to be possible. And that is a little bit then a bit of a concern, because I eventually want to end up with a QMI so that I can use matrix S lemma. So it's not going to be immediate then, in the sense that it is, if I start formulating the data-based problem, it's not going to be in all of a sudden I'm going to be able to write the QMI. Okay. How can I continue then? Well, I use some standard matrix acrobacy from LMI theory. If you read books about linear matrix inequalities, there are always these matrix tricks. Something which doesn't look like an LMI is converted to an LMI, like Schur complement tricks Henk applied a couple of times yesterday, or there are other tricks. I call it matrix acrobacy, because you manipulate these matrices and so on. So now, to be able to write this as a QMI, I need to massage it a little bit, because it is not a QMI in AB. But we have some tools from LMI theory which can help us to write it as an LMI. First thing I do is, instead of A plus BK and C plus DK, I use AK and CK. Once A, B, C, D, and K are given, AK and CK are uniquely determined by them. Now, this star inequality is nothing but this inequality. Agree? So now, the idea is to manipulate this LMI in such a way that at the end I obtain a quadratic matrix inequality. First, I use Schur complement. I use Schur complement with respect to this block. Therefore, to begin with, that block needs to be positive definite. And the Schur complement is this term minus this term times inverse of this term, and finally the last term. Or maybe I can write this on the board once, because we are going to use it again and again. Henk has written even all other cases, but this matrix is positive definite if and only if gamma square I minus p is positive definite, and the Schur complement of the bigger matrix with respect to gamma square I minus p is positive definite. And this is the Schur complement. Well, you see there is this p times inverse of this times p term, and it is here. It's an algebraic manipulation. Okay? Now I continue, and I look at first gamma square identity minus p, and I multiply from left, and this means that multiplication from left by p minus half, and from right by p minus half. And if I define P inverse as Q, then I see that this is equivalent to Q minus gamma to the power minus 2I greater than 0. What about the bigger term? So this was the bigger term. Now, one can show that this term in the parentheses, in terms of Q, is equal to exactly this inverse of this term. Then we are looking at this matrix inequality. So P and Q are inverse of each other. What I'm going to do is now, I use Schur complement first. You may say, what Schur complement? This is a one block matrix. But if I look at this matrix, this term is nothing but the Schur complement of the bigger matrix here with respect to 2, 2 block. Now I multiply row blocks by Q, column blocks by the first row blocks by Q, first column block by Q, and then I obtain this one, and because Q times P times Q is equal to Q. Q is P inverse. But I have this K times Q term here, 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 and also here. If I define Q times Q as L, I am looking at this matrix inequality. It is still not linear. I can change variables P and K to Q and L, and that's what I did. But it is still not a linear matrix inequality. I take the Schur complement once more on this one with respect to this block, 1, 1 block, by defining CQL as CQ plus DL, this term. And then this needs to be positive, and the Schur complement with respect to that needs to be positive. But now, I observe the following. The last term, this one, is a QMI in A and B. So now, if I perform this multiplication, that is going to give me the left-hand side of this inequality. So basically, the starting point was a matrix inequality which cannot be cast as a QMI in terms of AB variables, but by massaging it, I obtained a QMI in terms of AB. Then I am in business. Now I'm going to start the data-driven setup. It is going to be very similar to feedback stabilization, but not the same, because there are also matrices C and D. I'm going to look at this true system. AS, BS, and W are unknown. W is a noise term. C and D are given. C and D are given, and they determine a to-be-controlled output. And the idea is, although I don't have AS and BS, what I know is, 1, there's a certain quadratic matrix inequality satisfied by W, and 2, I am given XU data. Now I can write down, as usual, the set of data consistent systems. And this, it is going to be this green, it's going to be given by this green quadratic matrix inequality. Agree? I'm going to now define informativity for H infinity performance gamma. I'm going to say the data are informative for H infinity control with performance gamma if there exists a feedback gain K and a positive definite matrix P such that this matrix inequality is satisfied for all AB in sigma. Well, I know from what I have done so far is that this equation 1 is satisfied by some P and K if and only if there is a positive Q and L such that this thing is positive and this thing is positive. But this thing is a QMI, the last thing. Now I can apply matrix S lemma. If I apply matrix S lemma, and if you, this was the scenario for feedback stabilization. Now I'm going to replace the blue one with this new blue one. I simply apply matrix S lemma, strict version, and then this is what I'm going to get. Data are informative. Of course, I need to make some assumptions because to apply this matrix S lemma, I need to guarantee that N22 is negative definite, and that can be guaranteed only if X minus U minus has full row rank and phi 22 is negative definite. Under these assumptions, the data are informative for H infinity control with performance gamma if there exists a positive definite, sorry. If there exists a positive definite Q, L positive alpha such that, to begin with, Q satisfies this, and then this bigger matrix inequality is satisfied. It is not linear, you may say, because we have the inverse here, but again, again, sure complement idea, sure complement argument would lead to linear matrix inequalities. Remember, CQL is linear in Q and L. So this is a linear matrix inequality now. So what is the lesson we should take from what I have shown about H infinity control? Well, to begin with, of course, we can solve H infinity control for data by using data only. But more importantly, if we have any other problem which is given, whose solution is given by certain linear matrix inequalities, we can convert it to a QMI in AB, and once we do it, we can use a matrix S lemma. And indeed, in the lecture notes, you can see, for instance, H2 control, suboptimal control, and so on. And the idea is always to use the same thinking. Are there any questions so far? Okay. This was the first part. Shall we have the break now or later? We can have the break. Yes. We are going to have a break. Question is whether there is a whether these conditions are essential or not. Indeed, you can drop these assumptions, and the cost is going to be that there is going to be another parameter beta in these LMIs. But I don't want to state the most general result because it's already technical, and you know. I don't want to make it even more technical. Any others? Let's have a break then.